isn't it convenient that your exam is due today when you have a professional day? You have a day off, when the school is on a professional day. That's very convenient, I suppose, because I haven't checked this morning to see how many of you have actually taken the exam. Really? It just told me I couldn't minimize while I'm recording. Okay, let me go in here and check real quick. And I don't want to do that. All right, well, I'm just mumbling to myself. If you haven't taken your exam, this is a reminder that the exam is due today at 5 p.m. I have had several of you take it. Thank you very much. And I've got a really good response this semester for college algebra for folks sending in their scratch paper. That's actually unusual for college algebra. Usually you don't send it in, but believe it or not, this can be extremely beneficial. I have given as easily 30 points partial credit before. Normally it's not that much. Normally it's between 10 and so points, but it is 10 points still. But I have given as much as 30 points partial credit just based on, and I understand there are lots of reasons why getting it from your piece of paper to my math lab can be an issue. It happens. I have seen people literally type the completely incorrect thing in the box when they have the correct answer circled on their paper. And I'm not sure, and I need to ask sometime what causes that? Why did you do that? Because I don't know what goes on there, but something happens from your paper to my math lab. So if you'll, as you do your test, try to be as neat as possible so I can find the problems and put a number by it. So at least I'll know what number you're working on. They don't necessarily have to be in numerical order. I know you don't necessarily do the test in numerical order, but if you can just number what problem you're working on and try to be as neat as possible so I can find it. If I can't find it on your paper, I'm not going to grade it. I just don't have the energy or time to do that. But if you'll, and then take a photo of it with your phone and then email that to me. You should be able to email that to me from your phone. You can either log into my Redlands and go to self-service and go to mail that way. Or if you have the mail on your phone, you have the mail app, you can do it that way. Whatever works for you. All right, are there any questions this morning? And I said that I am going to record this. I am recording this and I'll post this later today. I normally record, upload to YouTube to my private channel, and then post the link in Blackboard. All right, I am going to share my screen. And I believe today we're going to be working on section 2.2. If I can get a little bit farther than 2.2, I will do that because we do need to cover 3 sections this week. So let's see what we can do. All right. That is correct, Natasha. Final due date for all homework for chapter 1 and quizzes for chapter 1 and the review for exam 1 are due on the 24th. And I do make that review due on the 24th in case you take your exam late, then you can still have the review available for you to look at. Okay, so today I'm going to keep the chat up. Hopefully it'll stay up so I can see. Today we're going to look at section 2.2, and this is just a continuation of what we discussed in section 2.1, where we defined what functions are. And now we're just going to look for characteristics of functions. So we're going to look at where it increases or decreases. And every function, you do the review for a grade. It does count for a grade. And I do that because that's the only way I can get students to do it. When I didn't count it for a grade, nobody did it. I'm thinking doing your review before you take your exam is a smart idea. Okay, so every function has behavior when you graph it. So every function is either going to be increasing, decreasing, or constant over its domain. It's going to be one of those three, or it might be all of those. So we'll discuss when you look at the domain of a function, so domain is x values, what is the function value doing? Then we're going to talk about relative maximas and minimas, and those are actually related to where a function's increasing or decreasing, because maximas and minimas are where the graph of your function changes direction. Then we'll look at the test for symmetry. There is actually 3 tests for symmetry, depending on what symmetry you're testing for. And then we'll look at specifically even and odd functions that have unique symmetry. And then we'll talk about piecewise defined functions. And then I'm not sure why, but they tacked the difference quotient onto this section. I'm not sure exactly why this guy did the things he did, but the difference quotient is important as you move forward in STEM. It's one of the very first things you do in calculus is the difference quotient. Okay. All right, so in the days of COVID, this is actually fairly realistic, isn't it? So you wake up one morning and you have a fever. You don't feel well, so you decide to take your temperature. And you take your temperature and it's 101 degrees. So that is above average, which is what, 98.6 or whatever it is. And then perhaps you take an Tylenol or something like that. And over the next 3 hours, so over the next 3 hours in our domain, so from, and I'm sorry, you're going to see the lights. I think I'll turn my video off. Stop that video so you don't have to see me. So over the next 3 hours in the domain, from the time you wake up to 3 hours later, so 3 hours over the domain, your temperature goes down, your temperature decreases. So over this time period, you actually have a decrease in temperature and you start feeling better. Okay. So over this time period in the domain, whoops, from 0 to 3. So when you wake up, we'll take that as time 0. And 3 hours later would be 11 a.m. Your temperature goes down. So at that time, you take your temperature again, and it's normal. It's 98.6. But over the next 2 hours in your domain, come on, pen, cooperate with me. Over the next 2 hours in the domain, from 3 to 5, your temperature goes back up. And so 5 hours into your domain, or from 3 to 5, your temperature goes up from normal 98.6, it goes back up to 100. So over the interval in your domain from 3 to 5, your temperature increases. Then from 5 in your domain to 7 in your domain, so from 5 to 7, your temperature remains a constant at 100. So in your domain, from time 0 to time 3, your temperature decreases. So as time moves forward, or as time increases, your temperature goes down, your temperature decreases. So as X increases, Y decreases. And then over the interval from 3 to 5, let's actually put brackets on these, why not? From 3 to 5, your temperature goes back up, it increases. So as X gets bigger, X goes from 3 to 5, X gets bigger, so does your temperature. Your temperature gets bigger also, it goes up. So as X increases, if Y increases, that means your function is increasing. And then from 3 to 5, I said put brackets, I don't want brackets, I want parentheses. And I'll explain that in a minute. And then over the next couple of hours, your temperature doesn't go up at all, it stays the same. So your temperature is constant. So as X increases, Y remains constant, then your function is constant over that interval. So my function is decreasing from 0 to 3. It's increasing from 3 to 5, and it's constant from 5 to 7. And I originally put brackets, which is a mistake. It should always be parentheses, because when you're talking about where a function's increasing or decreasing, it's doing neither at a point. At a point, for example, at X equals 5, X equals 3, your temperature is 98.6. That's neither increasing or decreasing at that point. At time X equals 5, your temperature is 100 degrees. It's not increasing or decreasing at that point. So beyond that point, it's doing something, but at that point, it has a value. So here's the formal definition for increasing and decreasing. A function's increasing over an open interval, and I highlighted this in red and made it bold because this is actually quite important. Whenever you're talking about where a function's increasing or decreasing or constant, you're always talking about over an open interval. So you never use equals. You always use parentheses or less than or greater than. A function's increasing on an open interval if f of x1 is less than f of x2 whenever x1 is less than x2 for any x1 and x2 in the interval. So what this means is at x1, the function value is smaller than it is at x2. And x1 is also smaller than x2. So this means the function's going up. It's rising from left to right. A function's decreasing over an open interval I if f of x1 is greater than f of x2 whenever x1 is less than x2 for any x1 and x2 in the interval. So what does this mean? This means that the function value f of x1 is larger than the function value at f of x2. So it's above f of x2. So it has to go down as it moves from x1 to x2. So that's a function that's decreasing in that interval. And it's constant if the function values are constant for any x1 and x2 in that interval. So it goes down, it's decreasing, it goes up, it's increasing. If it's horizontal, it's constant. We never use brackets when we describe where a function's increasing or decreasing or constant. We always use parentheses. Okay, so where is this function increasing, decreasing, or constant? So if we look at this function, as I said a minute ago, maximas and minimas are actually points where our function changes direction. And those are these little hills. Okay, come on, PowerPoint, cooperate. These little hills and these little valleys, that's where your function changes direction. So I think I'll just minimize that for now. So if I look at this function, I can see that at -1, x is -1. Thank you. That this function changes direction. And I can also see that at x equals +1, this function changes direction. So leading to the next slide, this is a little maximum. We call that at -1 a relative maxima. And at +1, that's a little valley. So that's a relative minima. It's where your function changes direction. So now I can look at my graph and I can separate my coordinate plane into intervals. So at -1, x equals -1, it does something. At x equals +1, it does something. So our intervals look like this. We have an interval to the left of -1. To the left of -1, my function is doing something. So let's label that. And then between -1 and +1, my function is doing something. So let's label that interval. And then to the right of +1, my function is doing something. Okay, so what is my function doing? Well, to the left of -1, to the left of -1, this function is going up. So as x is getting bigger, so as x, PowerPoint is not helping me this morning. As x is getting bigger, so is y. So if as x gets bigger, y gets bigger, the function's increasing over that interval. So our function is increasing in the interval from -infinity to -1. And then at -1 to +1, it does something. Okay, at -1, it's increasing, but at -1, it changes direction and it starts decreasing. So in this interval here, x is getting bigger, so x is still increasing, but y is decreasing. So y is going down. So in the interval, from -1 to +1, this function is decreasing. And then if we look at what happens to the right of +1, this function starts increasing again. Because again, as x is getting bigger, so x is increasing, y is also increasing. So in the interval from 1 to infinity, this function is also increasing. And I can't remember, I do believe my math lab just wants you to separate those intervals using a comma. Can you still hear me? My computer's doing weird things. All right. And be sure you read the instructions when you're doing these problems in my math lab. I'm pretty sure in this particular type of problem, if you have more than one interval where it's increasing or decreasing, they just want you to separate those by using commas. Okay, so this leads us to the definition of relative minimas and relative maximas, or maximums and minimums. So if we look at this graph here, we can see that at x equals b and x equals a, this function does something. It changes direction. So to the left of b, or from negative infinity to b, this function's decreasing. It hits this value of b and it changes direction and it starts increasing. So where a function goes from decreasing to increasing, that's a relative minimum. Okay, now the other way you can look at this, and the way they define it, is that at x equals b, the value of this function is f of b, whatever the value is when you substitute b in for x. But on each side of b, the value of the function's bigger than it is at b. So to the left of b, y is bigger than at b. To the right of b, y is bigger than it is at b. So that is a relative, or we also use the word local minimum. So this function increases until it hits the value x equals a. And at x equals a, this function changes direction again. It goes from increasing back to decreasing. So that is a relative maximum. Again, at the value a, x equals a, the value of the function is f of a. So whatever a equals, you'd plug that in and you'd get a value for your function. But on each side of x equals a, the value of the function is less than it is at a. So to the left of a, the value of the function is smaller than it is at a. And to the right of a, the value of the function is less than it is at a. So that's a relative maximum. A minimum is a little valley in your function. A maximum's a little hill in your function. Now, this particular function doesn't have an absolute maximum or minimums because of the arrows. This thing continues unbounded to the right and to the left. So it doesn't have anything that's absolute. And this book doesn't really spend any time talking about absolute maximums or minimums. Okay, so this is a sine function. In case you've taken trig, you might recognize this. So what's this function doing? This function is coming from the left over the domain from negative infinity to pi over 2. And at negative pi over 2, sorry about that, get the sign right. And at negative pi over 2, this thing changes direction. So it's decreasing from negative infinity to negative pi over 2. It changes direction at negative pi over 2. So it has a relative minimum of -1 at negative pi over 2. So maximas and minimas are y values. So they're a y value at an x value. So this thing has a minimum of -1 at x equals negative pi over 2. Okay, so then it increases until it reaches pi over 2. So from negative pi over 2 to pi over 2, it's increasing. And at pi over 2, it changes directions again and starts decreasing again. So it's decreasing from pi over 2 to infinity. But at pi over 2, it has a relative maximum. So it has a relative maximum of 1 at x equals pi over 2. All right, so back to this example that we had a little while ago, and I already described that these were maximas and minimums, maximums and minimums, and we do need to have a value here. It's kind of hard to see what this value is. Let's say this is -2. Let's say this is +2. I do need to know this. So again, this is the same function we looked at a minute ago. This function is increasing from negative infinity to -1. So in the interval to the left of -1, it's increasing. At -1, it starts decreasing. So it's going to have a maximum of 2 at x equals -1. Then it changes direction, it decreases from -1 to +1. So over the interval in the domain from -1 to +1, it decreases. And it's going to have a minimum then of -2 at x equals +1. And then to the right of +1, that function increases. So it increases without bound from 1 to infinity. Okay, I don't want to spend a lot of time talking about Denzel Washington. I should probably take these slides out because for time, I just don't have time to talk about Denzel. But briefly, the reason they have this slide in here is because apparently, and I mean, I have always known he's a pretty good looking chap, but apparently Denzel Washington's face is perfectly symmetrical, which is one of the things that human beings look at other human beings as aesthetically pleasing. So if your face is symmetrical, that is pleasing to the human eye. And his face is perfectly symmetrical. So if we draw a y-axis down the middle of his face, and an x-axis is purely arbitrary. If you look at his eyes are exactly the same distance from that vertical axis. And the bridge of his nose, his nose and his lips and all that stuff are perfectly symmetrical. So this leads us to our symmetry in algebra. So Denzel is symmetric to the y-axis. All right, what does that mean? That means if a function's symmetric with respect to the y-axis, on each side of the y-axis, you have a mirror image of your graph. So if we look at this first image here, and we look at the first quadrant, for this example, our graph is in the first and the second quadrant. But if we look at this, the second quadrant's image of this graph is a mirror image of the first quadrant's. So what this means is, if it's symmetric with respect to the y-axis, it doesn't matter if I plug in x or -x, it doesn't matter. As soon as I plug in x, I get a y. If I plug in -x, I also get y. So it doesn't matter if I plug in x or -x, I output exactly the same thing. So that's symmetry with respect to the y-axis. Now, symmetry with respect to the x-axis is not a function. But what this means is it doesn't matter if I plug in x. Well, if I plug in x, I get a y or a -y. So it's not a function. You can't plug in an x and get two different y's and it be a function. So what it means for us for our test of symmetry is that it doesn't matter if I put a y or a -y into the equation of this function, I get it, it doesn't matter. So if I put in y or -y, it doesn't affect the function at all. Okay. And then origin symmetry is a little bit maybe trickier. If I draw a line through the origin to this point, this is some distance d. If I draw a line in the opposite direction, the same distance away, I'm going to hit another point. Now, for our test of symmetry, what this means, if I plug in x, I output y. But if I plug in -x, I output exactly the opposite of y. So if I plug in x, I output y. If I input -x, I output -y. So this leads us to our test for symmetry. So what you do is you take your equation of your relation, because it may not be a function. take the equation of your relation and replace x with negative x. And if you get exactly the same equation you started with, then that is symmetry with respect to the y-axis. If you replace y with negative y, and you get exactly the same equation you started with, that's symmetry with respect to the x-axis. That's not a function. If you replace negative x for x and negative y for y, and you get exactly the same equation, then that's symmetry with respect to the origin. So let's see if we can't give an equation a test. So we're going to test x equals y squared minus 1. We're going to test for symmetry with respect to the y-axis, for symmetry with respect to the x-axis, and then symmetry with respect to the origin. So let's do y-axis first. So I'm going to replace x with negative x. So where there's an x, I replace it with negative x. So here is my new equation. This is the equation I got when I replaced x with negative x. And here's my original equation. And I compare. Are these two equations identical? So is this equation completely and totally identical to this one? I mean, are they exactly the same thing? And the answer is no, they are not exactly the same thing. Because if we look at this, the new equation has a negative x. The original equation has a positive x. So they are not the same equation. So it actually makes a difference if you replace x with negative x. You get something different for y. So because of that, this is not symmetric with respect to the y-axis. Okay, so that's how we test for symmetry with respect to the y. To test for symmetry with respect to the x, we're going to replace y with negative y. So our original equation is x equals y squared minus 1. We're going to test for x-axis symmetry. And to do that, we're going to replace y with negative y and see what happens. Well, I know for that first term on the right-hand side of this equation, I have y squared, so it doesn't matter if I put in a negative or positive, that's going to be positive. Whenever I square a negative, I get a positive. When I square a positive, I get a positive. So it looks like this. Okay, so now my new equation is x equals y squared minus 1. My original is x equals y squared minus 1, and those are identical. So we do have symmetry with respect to the x-axis. So this is not a function. And we knew this wasn't a function before we ever began, because remember from last week, if you have an even power on your y, that's not going to be a function. Okay, now let's test for symmetry with respect to the origin. So we replace x with negative x and y with negative y. And I'm pretty sure this is not going to work. We're going to get negative x equals negative y squared minus 1. Negative x equals y squared minus 1. That is not the same as our original equation. So this does not have symmetry with respect to the origin. Okay, so no symmetry to the origin. And as a matter of fact, if you look at the graph of this thing, this is a laid over parabola. So it looks like this, and you can see, I think, from the graph that there is symmetry with respect to the x-axis. If I put x equals 2 in my equation, I get two different values for y. Okay, not a function, can't put this one x in and get two different y's. All right, so looking at our previous example, looking at this example, we know that symmetry with respect to the y-axis is a function, and symmetry with respect to the origin can also be a function. So we're going to give those special names. If a function is symmetric with respect to the y-axis, that is an even function. So if it's symmetric with respect to the y-axis, it's even. And the way you test for this is you replace x with negative x. And if the function is the same after you do that, so f of negative x equals f of x, then it is an even function. Now, an odd function is symmetric with respect to the origin. So how we test for that is we replace f with negative x, and if we get the exact opposite of the function we started with, then we know that this is symmetric with respect to the origin. So if I replace negative x with x and nothing changes, so I replace x with negative x, but I output the same y, that's symmetry with respect to the y-axis. That's an even function. If I replace x with negative x, and I get exactly what the opposite of what I started with, so I replace x with negative x, and I output negative y instead of positive y, that is symmetry with respect to the origin. So let's conduct a test. First, let's look at our quintessential even and odd functions. These are our quintessential because these are two of our standard 7 functions. This is the standard quadratic function. The standard quadratic function f of x equals x squared is an even function. It is symmetric with respect to the y-axis. This is our quintessential odd function. It is the cubic function, one of our 7 basic functions that we need to know the shape of, what it looks like. And it is an odd function because if I input x, I output y, but if I input negative x, I output negative y. If I input 2, I output 8. If I input negative 2, I output negative 8. If I input 3 over here, I output 9. If I input negative 3, I also output 9. That's even. So let's look at a graph here. A is symmetric with respect to the origin. I have some point x, y here. Down here, I have some point negative x, negative y. That is symmetry with respect to the origin. This is odd. This is an even function. We have symmetry to the y-axis. I have some x, y here. I have some negative x, y here. And this is neither. So if your function is neither even or odd, if it doesn't have any symmetry with respect to the y-axis or the origin, then it is considered neither even or odd. Okay, so how do you conduct the test? To conduct the test for even or odd, replace x with negative x. So evaluate your function at negative x. Okay, so it does h of negative x equal h of x. So does negative x to the fifth plus 1, does that equal x to the fifth plus 1? And the answer is no. They're not the same. The function, the left-hand side of this equation has a negative here. There's not a negative on the right-hand side of the equation in front of the x to the fifth. So this function is not even. Okay, does h of negative x equal negative h of x? Okay, well, what's negative h of x? Negative h of x is negative x to the fifth plus 1. So take the entire expression that defines your function and change its sign. All right, so now does h of negative x equal negative h of x? Does negative x to the fifth plus 1, does that equal negative x to the fifth minus 1? And the answer is no. They are not equivalent. So this function is not odd. So if it's not even and if it's not odd, it's neither. Now I encourage you, you bought $100 and something calculator. I encourage you to take that calculator out and graph this. And I think you could look at the graph and you could determine that this is not even or odd, even without the test. It helps just to take a look at it. It looks something like this. Something like that. So it's not going to be even or odd. There is no symmetry with respect to the y-axis, no symmetry with respect to the origin. Okay, piecewise functions. Piecewise functions are actually very common. For example, if you have utility bills or your parents have utility bills, frequently your electric bill or your water bill or gas bill are piecewise defined functions. Up to a particular usage, which is the example we have here of a phone plan, they charge you a certain rate. And then when you go over that amount of that usage, that amount, they charge you a different rate. So that's a piecewise defined function. In our example, it's a phone plan. So what this phone plan does is it allows you to talk up to 60 minutes and it only charges you a flat fee, or it charges you a flat fee for the first 60 minutes, charges you $20. So over the domain, if you talk 0 minutes up to and including 60 minutes, they charge you $20. Now, as soon as you talk over 60 minutes, if you talk 61 minutes, then they're going to charge you a per minute rate. So they're going to charge you the $20, but then they're going to charge you per minute over 60. So each additional minute over 60 minutes is going to cost you 40 cents a minute. So for any time greater than 60 minutes, you're going to get charged using a different formula. So this is the way we write this. So our function, our cost function's equal to, it's equal to two different things depending on the usage. So it's $20 flat rate if you talk anywhere from 0 to 60 minutes inclusive. So if you talk no minutes, you're going to get charged $20. If you talk 15 minutes, you're going to get charged $20. Up to, if you talk 60 minutes, you're going to get charged $20. After that, they're going to charge you per minute. So they're going to take how many minutes you talk above the 60. So if you talk 62 minutes, it would be 2 minutes. They're going to multiply that by 0.4, 40 cents, and then they're going to add that to the 20. So anywhere in the domain, if you're greater than 60, they're going to charge you based on the second equation. So there are two different equations that define your cost based on where you are in your domain. That is a piecewise defined function. You have different equations that define your output over different intervals in your domain, your input. And this is what the graph looks like. From 0 to 60, it's constant. And at 60, it's a line with a slope that's not 0. A piecewise defined function is a function that is defined by two or more equations over a specified domain and is called a piecewise defined function. So how do you evaluate a piecewise defined function? Well, it depends on where you are in the domain. So what's C of 40? Well, according to my definition of this function, if my input value is anywhere between 0 and 60, my output is the constant 20. So if my input is between 0 and 60 inclusive, then my output is 20. But now, what if my input is more than 20? If my input is 80, so my input is greater than 60. Well, if my input's greater than 60, then I use the second equation to evaluate this function. So C of 80 would be 20 plus 40 cents times 80 minus 60. And I believe that's 32. Get my notes out here. 28, not 32, 28. I could probably do that in my head. 0.4 times 20 is 8. 20 plus 8 is 28. Okay, so that's a piecewise defined function. Well, how do you graph these things? Well, I graph them in two parts. And I graph first over the first part of the domain. So I'm going to graph f of x equals 3 for everything less than or equal to -1. So -3 or -2 or -1, anything that's less than -1. Well, I actually happen to know that the output's 3. So for anything to the left of -1, including -1, this function's constant. So the output is 3 no matter what the input is. So my ordered pairs are -3, 3, -2, 3, and -1, 3. So here's the tricky part. When I start graphing the second part of this, the second piece of this, I always graph it for where this interval starts, even though -1 is not included in that interval. I am going to graph it at -1, but this is going to be a hole. So this is actually going to be an open circle on my graph. So at -1, f of -1 is -1 minus 2. Is that -3? And then maybe do 0. I'm doing stuff to the right of -1. So 0 minus 2, and then maybe do 1. F of 1 is equal to 1 minus 2. Is that -1? Okay, so now I have 6 points that I can plot. I can plot the 3 points that are to the left of -1, including -1. And then I can plot 3 points to the right of -1. And I am going to have a hole, an open circle at -1, -3. All right, so let's go plot those points. So I had -1, 3, -3, 3, which is right there. I had negative 2, 3, and negative 1, 3, and those are all solid dots. There is a solid dot at negative 1. So anything to the left of x equals negative 1 is going to be constant. Then I had negative 1, negative 3 on the other piece, and that is an open circle. Then I had negative 2, 0, negative 2, and 1, negative 1. So we're going to draw a line through that. So that's what the graph of my piecewise defined function looks like. And again, we have a hole here because the domain is x is greater than negative 1. Okay, what's the domain and range of this thing? That's kind of tricky. Okay, I think the domain, when you're looking at piecewise defined functions, I think the domain is the easier of, which is typical, the domain is the easier of the two to figure out. Okay, so if we look at this thing, and if matter of fact, if we were to draw these two intervals on a number line, we have this and we have this. So if we join those two intervals, I think you can see that the domain is the set of all real numbers. Pretty straightforward. The range is a little trickier. So again, when you're looking at the range, look at where the graph starts in the y direction and then where does it end. And in this particular case, we can kind of ignore this over here. Not always the case, but in this case, we can. Because over there to the left of negative 1, the function's values are constant, it's 3. But if we look at this part of the graph, the right-hand part, we can see that this function starts at negative 3, and it goes to, it's unbounded in the vertical direction. So the range actually goes from negative 3 to infinity, because it's unbounded in the vertical direction. And the minimum value right here, this minimum is negative 3. So it starts at negative 3 and it goes to infinity. Okay, all right. The difference quotient. The expression f of x plus h minus f of x divided by h for h not equal to 0 is called the difference quotient of the function f. And what this represents for those of you who've taken calculus, we draw some function here on the coordinate plane. And we have a point on our coordinate plane, x, then an itty bitty more than x is x plus h. And if we look at the value of the function at f of x plus h, and we take, this is called the slope, which we're going to talk about in the next section. If we find the slope of the line that connects those 2 points, we can find the rate of change, how much that the function changes from one point to the next, which leads us to the definition of the derivative. So this is pretty important stuff when as you move on in STEM. So the way I find the difference quotient is I do it in steps. Why not? So I need to find f of x plus h minus f of x, the whole thing divided by h. So the first thing I do is evaluate my function at x plus h. So this means that in my function, wherever there's an x, I replace that with x plus h. So can I evaluate a function for anything? And the answer is yes, as long as that thing you're evaluating your function at is in the domain. This is a quadratic function. Its domain is the set of all real numbers. There's no real number. You can't plug in there and square it and multiply it by negative 2, add that number to it and add 5 to it. So the domain of this function, its domain is the set of all real numbers. So I can plug absolutely anything I want in for x. So x plus h is no problem. So we're going to plug in x plus h for x. Now I'm going to simplify this. I'm going to first square this binomial. I have x plus h squared. I'm going to use my formula. I square the first term, so I square x. I multiply x and h together, and then multiply that result by 2. So x times h is xh times 2 is 2xh. And then I'm going to square the h. Now I'm going to remove the parentheses by distributing the -2 across. Okay, so f of x plus h is -2x squared minus 4xh minus 2h squared plus x plus h plus 5. Now I'm going to take this expression and I'm going to subtract the original function from it. Then I'm going to take that result and divide it by h. So I'm going to take this expression and I'm going to subtract f of x. So I have -2x squared minus 4xh minus 2h squared minus x, plus x plus h plus 5. And I'm going to subtract the -2x squared plus x plus 5. So I'm going to subtract that entire expression. That's why I put it in parentheses. So I get -2x squared minus 4xh minus 2h squared plus x plus h plus 5 plus 2x squared, distributing that negative across, minus x minus 5. Now, if you've done this correctly, at this point, your original function and some value in the f of x plus h should add to 0. For example, the -2x squared added to plus 2x squared is 0. X minus x is 0. 5 minus 5 is 0. So what you're left with is terms that have a factor of h in it. So I have minus 4xh minus 2h squared plus h. And now we're going to take that result and divide it by h. So I can factor in h from the numerator and divide it with the h in the denominator. So the result is -4x minus 2h plus 1. That is the difference quotient. Now, in calculus, if I let h approach the number 0, so in other words, remember when I drew my little picture, this is x, this was x plus h. So h is just an infinitely bigger, infinitely small value. So x plus h is just infinitely bigger than x. So if I let the difference go down to 0, this h go down to 0, so the minus 2h goes away because it becomes 0, that's the derivative of that function up there. And the derivative is the instantaneous rate of change of a function. So the instantaneous rate of change, the derivative is minus 4x plus 1. You just learned calculus. And that is how simple calculus can be. It can be more complicated than that, but it can be as simple as that. All right, so that's the difference quotient. And that should be the end of that section. Doing good. I'm doing good. Doing good. I am going to start 2.3. I'm going to try to get good 10 minutes in here. Okay, because the next couple of sections, we're going to concentrate on linear functions. In section 2.4, we're actually going to do a little more of that prep for STEM. So we're going to do a little more prep for calculus, because instead of talking about the difference quotient, which we just did, which leads us to the derivative, we're going to talk about the average rate of change in section 2.4, which is one of the things we do before we talk about the derivative. So if you have 2 points on a curve, what's the average rate of change from point A to point B? Okay. But first, let's talk about lines. We're going to talk about linear functions. So this entire section only concentrates on linear functions. We're going to first look at lines and calculate their slope. And then once we have the slope, this is going to give us a couple of different forms of the equation of a line. We're going to get the point slope form, then we're going to get the slope intercept form, and then later we'll get the general form. So we have 3 forms of the equation of a line: point slope, slope intercept, and the general form. And then in between, we'll talk about the equations of horizontal and vertical lines. And then we'll talk about intercepts. You can use intercepts to graph from the general form of the line. And this is actually my favorite way of graphing lines. If the intercepts are nice integers, this is the best way to graph it. It's very easy. And then we'll look at a model. Okay, so this is called a scatter plot. So someone did a survey and they looked at the percentage of adult females who are literate, so they can read, and they looked at child mortality. Now, this does not necessarily mean that there's a cause and effect relationship between these 2 variables, but there's definitely a correlation between these 2 variables. So you can see that as the percentage of adult females who are literate increases, so as X goes to the right, the mortality of their children under the age of 5 goes down. And when they plotted all the data points that they got from this survey, they looked at it and said, huh, this looks kind of linear. So they take this data and they either put it in a computer, in Excel maybe, or your TI-84 calculator will do this. If you put the data points in your calculator, you can run what's called a regression on it. You can run a linear regression on it, and you can get the equation of the line. So this blue thing here, this blue line, is the model, the regression line that they got from their data. And what the regression line does is it draws lines very, very quickly. You can't even, it's so quick that it immediately spits out the answer when you put it in your calculator. But it draws lines until it gets a line that's evenly dispersed. It has the same amount of data distance above and below the line. So that's how it draws a regression. But it looks like, to me, that this data is fairly linear. And since it is linear and we can run a regression, we can get a model that models this data. Okay, so we might be interested in what is the steepness of this line? How much does it go down in the Y direction for a given amount in the X direction? And that is called the slope. So a slope is a useful measure of the steepness, and some higher mathematicians get really mad that we use the word steepness, but that is what slope measures. It measures how steep your line is, either going up or going down. So slope compares the vertical change, the rise, so how much your line is changing in the Y direction, versus how much it changes in the X direction. So it calculates the rise, how much it changes in the Y, divided by how much it changes in the X, the run. So the slope is a ratio of this change in Y over this change in X, or the rise over run. So if we have 2 points on a line, so this is a line, it's a straight line, and we have 2 points on it, then we can calculate this ratio of the change in Y over the change in X. So if we start at X1, Y1, and we go to X2, Y2, then the change in Y is right here. Y2 is bigger than Y1, so we say that the change, the rise, is Y2 minus Y1. Okay, the run, or the change in X, X2 is bigger than X1. So the run, we take the difference, X2 minus X1. And the ratio of the change in Y over the change in X, the rise over the run, is the slope. So the slope is calculated by finding the change in Y over the change in X given 2 points on the line, on a graph of a line. So here's your definition of slope. The slope of a line through the distinct points X1, Y1 and X2, Y2. We use the letter M to designate the slope. It's the change in Y over the change in X, or the rise over the run, or Y2 minus Y1 divided by X2 minus X1. X2 minus X1, that difference in the denominator cannot be 0. Can't divide by 0. Okay, so how do we find the slope given 2 points on the graph of a line? Well, it's a simple matter of plug and chug. So to find M given 2 points, 4, -2, and -1, 5, we're going to plug it in. And I always just kind of tell myself, I'm going to let this be the first point. So this is X1, this is Y1, this is X2, this is going to be Y2, and then I plug in. So it's going to be 5 minus a -2 over -1 minus 4. So that is going to be 5 plus 2 over -5, which is 7 over -5. So we have 7 over -5, which we can also write as -7 over 5, which we can also write as -7/5. So all of those mean exactly the same thing. So 7 over -5, -7 over 5, -7/5, all the same number. All right, so what's this mean graphically? So let's plot our 2 points on the coordinate system. 4, -2 is right here. So our other point, -1, 5. Okay, so let's look at the rise over run here. Okay, so let's go from -1, 5 to 4, -2. So to get from -1, 5 to 4, -2, I have to go down 1, 2, 3, 4, 5, 6, 7. So I have to go down 7, or -7. And then I have to do what? Go over 1, 2, 3, 4, 5, right 5, or +5. So the slope is -7/5, -7 over 5, or 5 over -7. So because we could look at this in the opposite direction. So now what if I want to go from 4, -2 to 1, -5? Then I either have to go 1, 2, 3, 4, 5. So left 5. And I have to go up 1. I can't count. 1, 2, 3, 4, 5, 6, 7. So up 7. So the slope again would be 7 over -5. So either -7 over 5 or 7 over -5 or -7/5. Okay, so you have 4 different types of slope. If your slope is a positive number, then your function is increasing. It's going up from left to right. If your slope is negative, then your function is decreasing. If your slope is negative, your function is decreasing or it's falling from left to right. If your slope is 0, that is a constant function. So constant functions, the y values are all the same. So since the y values are all the same, the numerator of your slope equation is 0. So that is slope 0. And a vertical line has undefined slope because x2 equals x1 everywhere on that line. So the denominator of your slope equation is 0. So that's undefined slope. And that's so undefined. It's not a function. It's like so not a function. Vertical line is the quintessential not a function. So it's not a function and its slope is undefined. Okay, I think that's a good place to quit for the day. We'll pick up here on Wednesday. I did record this. For those of you who came in late, I apologize for not getting the link out earlier. And I'll post this recording later in the day. Did everybody get their name typed into chat who came in? All right, well, if everyone has their name typed into chat, then I'm going to go and let you